In this video, we're going to take a look at how to apply the characteristics of the sampling distribution of the sample mean, specifically when we sample from the normal distribution. So the underlying distribution of our population is the normal distribution, and it's a symmetric bell-shaped distribution. The population mean is mu, and the population standard deviation is sigma. So if we take random samples from this population and calculate the sample mean, we find that the sampling distribution of x bar is also the normal distribution with a mean of mu and a standard deviation of sigma over the square root of n. So we can see that the graph of the sampling distribution of x bar is taller than the graph of x, and this is because we find that the standard deviation of x bar decreases the spread or the variability of the values, and therefore they are more clustered towards the mean in comparison to the standard deviation of the population, which is simply sigma. The population mean interest charged on clothing accounts by a leading retail firm in 2012 was 183 Rand. And we've been told to assume that the population standard deviation of interest charged is 50 rands and that the interest charges are normally distributed. So we're going to take a look at 4 different questions and calculate the probabilities that are required. So in question A, what is the probability that a randomly selected interest charge is within 8 rand of the population mean? So in this case, since the question makes reference to a randomly selected interest charge, then we're going to define our random variable, and we're going to use x, which is equal to the interest charge on a clothing account in rands. So x is normally distributed with a mean of 183 rands and a variance of 50 squared, and this we get from the information that was given. So going back to what the question has asked us, we need to find the probability that x is within 8 rand of the population mean. So this tells us that as the population mean is your starting point, then x can be at most 8 units away from the population mean. So x can be at most 8 units larger or 8 units smaller. So therefore you find that the difference between x and mu will be at most 8 and at least minus 8. So then we have the probability that x minus mu is between 8 and negative 8 and positive 8. So on the graph you can see that you have mu right in the middle, and the lower boundary will be minus 8 units and the upper boundary will be at most 8 units. So now when we get to standardize, we see that the mean has already been subtracted from the numerator. So the only thing we need to do is to divide by the standard deviation of 50 from the notation here. So we end up with our z value in the middle, and we standardize only by dividing by 50 on both sides of the inequalities. So we find that the probability now becomes the probability of z between minus 0.16 and positive 0.16. We rewrite this as the probability of z less than 0.16 minus the probability of z less than minus 0.16. And we can head to the tables and find our 2 probability values. So this will give us 0.5636 minus 0.4364 in order to get our final answer of 0.1272. In question B, what is the probability that the mean interest charge for a sample of 10 retail customers is within 8 rand of the population mean? So the main focus in this question is on the mean interest charge for a sample of 10 retail customers. So that means that now we are looking at the sample mean. So we'll define our random variable, and this is x bar, which is the average interest charge on a sample of 10 retail accounts in rands. And we find that x bar has a normal distribution with a mean of 183 and a variance of 50 divided by the square root of 10 squared. So now going back to the question, we need to find the probability that x bar for a sample of 10 retail customers is within 8 rand of the population mean. So this tells us that X bar can be at most 10 units larger than the population mean or 8 units less than the population mean. So now X bar minus mu can be at most 10 or it can be at least negative 8 units. So this gives us our probability statement. So the probability we're looking for is that X bar minus mu will be between minus 8 and positive 8, keeping in mind that mu is going to be the mean right here on the graph. So we can be 8 units above or 8 units below in terms of this difference. And as you can see, we've already taken out the mean at the top. So when it comes to standardizing, we only need to divide by the standard deviation of X bar on either side. So we find that now we have the probability of Z between minus 0.51 and positive 0.51. So we can rewrite it and we have it as the probability of Z less than 0.51 minus the probability of Z less than minus 0.51. And we head to the table to find both the probabilities. So from the positive table, we find the probability of Z less than 0.51 is 0.6950. From the negative table, the probability of Z less than minus 0.51 is 0.3050, and the difference between the two gives us our final answer of 0.39. In question D, what is the probability that the sampling error of the mean is more than 8 rand? So the sampling error, we need to remember this is the absolute difference between X bar and mu. So our random variable of interest is still X bar, and X bar has a normal distribution with a mean of 183 and a variance of 50 divided by the square root of 10 squared. So this is equal to the probability of the absolute difference between X bar and mu being greater than 8. And by making use of the absolute relationships, we find that this is equal to the probability of X bar minus mu being less than minus 8 plus the probability of X bar minus mu being greater than 8. So on our graph, the first probability is the area to the left of 175, and the second probability is the area to the right of 191. So this, when we standardize, we're going to divide by the standard deviation of X bar. So now this will give us the probability of Z less than minus 8 divided by 50 over the square root of 10 plus the probability of Z greater than positive 8 divided by 50 over the square root of 10. So this is equal to the probability of Z less than minus 0.51 plus the probability of Z greater than 0.51. So from the tables, we find the two probabilities, we substitute them and find that our final answer is 0.61. So the probability of Z greater than 0.51 will be 1 minus the probability of Z less than 0.51. So that will be 1 minus 0.6950. And we have our final answer as 0.61. Now, in the following question, we have the salaries of managers come from a population where the mean is equal to 51,800 and the standard deviation sigma is equal to 4,000. So now the question says calculate the probability that the salary of a randomly chosen manager will be within $500 of the population average. Assume that salaries are normally distributed. So in this case, we're interested in the salary of a randomly chosen manager. So we can define our random variable X as the salary of a randomly chosen manager in dollars. And X is going to have a normal distribution with a mean of mu X and a variance of sigma squared X, and mu X is the expected value of X, and this was given in the information as 51,800, and the standard deviation sigma X is equal to 4,000. So the probability that the salary will be within $500 of the population average is the probability that X will be between 51,300 and 52,300. So this is equal to the area on the graph that has been shaded. And this is the area between 51,300, which is the mean, minus 500. And the upper value is 52,300, which is the mean, plus 500. So this is equal to the probability of 51,300 minus the mean, 51,800, divided by the standard deviation of 4,000, less than x minus mu divided by sigma, which is less than 52,300 minus the mean divided by the standard deviation. So this is equal to the probability that Z is between minus 0.13 and positive 0.13. And this is written as the probability of Z less than 0.13 minus the probability of Z less than minus 0.13. So the difference between these two probabilities is equal to 0.1034, and that is equal to the area between our two values. So in this question, calculate the probability that the average salary for a sample of size 100 managers will be within $500 of the population average. So we can clearly see that we are now interested in the average salary for a sample of size 100. So going back to the initial information, we can define X as the salary of a randomly chosen manager in dollars, and X has an unknown distribution with a mean of 51,800 and a standard deviation of 4,000. So if we define X bar as the average salary of a sample of 100 randomly chosen managers in dollars, we can see that as a result of the sample size being very large and greater than 30, then we can make use of the central limit theorem and therefore find that the sampling distribution of X bar will be approximately normal with a mean of 51,800, which is the same as the population mean, and a variance of 4,000 divided by 100 squared, divided by the square root of 100 and then squared. So the probability of X bar between 51,300 and 52,300 is the area on the graph that is between the two values, and the values are obtained by taking the mean 51,800 and subtracting $500 to get the lower value and adding $500 to the mean to get the upper value. So this is standardized by taking away the mean on both sides, and the mean is 51,800, and we divide by 400, which is the standard deviation of X bar. So this is equal to the probability of Z between minus 1.25 and positive 1.25. And this is equal to the probability of Z less than 1.25 minus the probability of Z less than minus 1.25. So the difference between the two probabilities gives us our final answer of 0.7888. Calculate the probability that the salary of a randomly chosen manager will be within $500 of the population average, and we're told to assume salaries are normally distributed. So in this case, we can see that we are making reference to the salary of a randomly chosen manager. So that implies that we're going to use the random variable X. So let's define X as the salary of a randomly chosen manager, and X has a normal distribution with a mean of 51,800 and a standard deviation of 4,000. So in this case, our probability statement will be the probability of X between 51,300 and 52,300, since we have $500 within the population average. So this will be equal to norm.dist, and in brackets it will be 52,300, which is your X value, comma 51,800 your mean, comma 4,000 your standard deviation, comma true, since we want the area to the left of 52,300, minus norm.dist in bracket 51,300, the value of x, comma 51,800 the mean, comma 4,000, comma, which is the standard deviation of x, comma true, since we want the accumulated area to the left of 51,300. So this will be equal to 0.0995. And if we compare to the value that we just calculated in the previous example, then we find that this value differs from the one we calculated, since in this case, the Excel functions makes use of the exact z-score, whereas in the previous example, we rounded up the z-score to 2 decimal places, so that created a bit of discrepancy. So in general, when we make use of the norm.dist function, we find that the first entry is your x value, then your mean in the second entry, your third entry is the standard deviation of x, and finally, your cumulative statement will be true since we're interested in the area to the left of x. Now let's calculate the probability that the average salary will be within $500 of the population average for a sample of size 100. So now we're interested in the average salary. So that means we're looking at X bar, and it needs to be within $500 of the population average, and the population average remains the same. And we have a sample of size 100. So the first thing is to define X bar. So this is the average salary of a sample of 100 randomly chosen managers. And we can clearly see that our sample size is very large, it's 100, so it's at least 30. Therefore, we can make use of the central limit theorem, and X bar will have an approximately normal distribution with a mean that is equal to the mean of the population, 51,800, and a variance of 4,000 divided by the square root of 100 all squared. So our probability statement will be the probability that X bar is between 51,300 and 52,300, since we have $500 within the mean. So which means we'll be $500 below the mean and $500 above the mean. So this is equal to norm.dist 52,300, which is the value of X bar, comma 51,800 the mean, comma 4,000 over square root of 100, the standard deviation of X bar, comma true, since we're interested in the area to the left of 52,300, minus norm.dist, and in the brackets it will be 51,300, the value of X bar, comma 51,800 the mean, comma 4,000 over the square root of 100, which is the standard deviation of X bar, comma true, since we once again want the area to the left of 51,300. So this gives us a final answer of 0.7887, and this is very similar to the one we found in the previous example, simply because in the previous example we used the exact z-score that we found, and this would give us the same value as we did, or close enough as we did, by using the Excel functions. So in general, when we make use of the norm.dist function, the first entry will be the sample average X bar. Then the next entry will be mu, which is your population mean, and it's equivalent to the mean of X bar. Then sigma X bar, which is the standard deviation of X bar. And finally, your cumulative statement will be true, since we're interested in the area to the left of X bar. In this question, we've been given that X is normally distributed with a population mean of 60 and a population standard deviation of 10. Furthermore, the probability of X bar lying between A1 and A2 is equal to 0.95, and the sample size is equal to 100. So we can see that our random variable of interest X bar has a normal distribution with a mean of 60 and a variance of 10 divided by the square root of 100 all squared. So the question asks, what are the values of A1 and A2? So from the graph, we can see that the mean of X bar is 60 and the values of A1 and A2 are placed such that 0.95 represents the middle 95% of the data. So that means that the area to the left of A1 is 0.025 and that is equal to the area on the right of A2, which is also 0.025. So the first thing, in order to find A1, we need to know the area to the left of A1, and we can see from the graph that that is 0.025. So if we know this area, then we can look for 0.025 amongst the probabilities in the Z table and find the corresponding Z value. So from the Z table, we find 0.025 and therefore the corresponding Z value is minus 1.96. And in the same way, we look for the area to the left of A2 and that is going to be 0.95 plus 0.025 and that gives us 0.975. So from the Z table, we look for the probability 0.975 and we find that the corresponding Z value is 1.96. So now that we have the two Z values, we can work our way backwards and find the values of A1 and A2. So using the definition of Z, we find that Z is equal to A1 minus mu divided by the standard deviation of X bar, sigma X bar. So in order to find A1, the Z value from the table was minus 1.96 and this is equal to A1 minus the mean 60 divided by sigma X bar, which is 1. So when we solve for A1, we find that A1 is equal to minus 1.96 times 1 plus 60 and this gives us a final answer of 58.04. And in the same way, Z is equal to A2 minus mu divided by sigma X bar. And in this case, Z is 1.96 and this is equal to A2, which is missing, minus the mean 60 divided by 1. So solving for A2, we find that A2 is equal to 1.96 times 1 plus 60 and we have our final answer of 61.96. Now let's calculate the values of A1 and A2 by making use of our inbuilt Excel functions. So since X bar has an approximately normal distribution with a mean of 60 and a variance of 10 over square root of 100 all squared, then we're going to make use of the norm.in function. So for A1, we know the area to the left is 0.025. So in order to get A1, it will be equal norm.in, and in brackets, the first entry is the area to the left, which is 0.025, comma 60, which is the mean, comma 1, which is the standard deviation of X bar, and this gives us a final answer of 58.04. And similarly, the area to the left of A2 is 0.975. So using the same formula, A2 will be equal norm.in and in brackets, it will be 0.975, comma 60, comma 1. And this gives us 61.96. So in general, when we want to make use of the norm.in function to find a percentile, then in the brackets, the first entry will be the area to the left, comma the mean of the X bar, comma the standard deviation of X bar, and this will give you the missing percentile. Now we're given that sigma X bar is equal to 25. What is the probability that the sampling error of X bar is less than 5? So in this case, we start off by defining the sampling error of X bar, and the sampling error of X bar is the absolute difference between X bar and mu. So our probability statement will be the probability of the absolute difference between X bar and mu being less than 5, and we're going to make use of the second absolute relationship here. So this is equal to the probability of x bar minus mu being between -5 and +5. And we keep in mind that z is equal to x bar minus the mean of x bar divided by the standard deviation of x bar. So this is equal to the probability of x bar minus mu divided by sigma x bar being between -5/25 and +5/25. And 25, keep in mind, is equal to sigma x bar. So this is equal to the probability of z between -0.2 and +0.2. And we can rewrite this as the probability of z less than 0.2 minus the probability of z less than -0.2. So from the table, the probability of z less than 0.2 is 0.5793, and the probability of z less than -0.2 is 0.4207, and the difference between these two values gives us our final answer of 0.1586. Here we're given that sigma x bar is equal to 25. What is the probability that the sampling error of x bar is greater than 10? So we need to remember that the sampling error is the absolute difference between x bar minus mu. So this means that we need to find the probability of the absolute difference between x bar and mu being greater than 10. And here we're going to make use of this first relationship. So this is equal to the probability that x bar minus mu will be greater than 10 plus the probability of x bar minus mu being less than -10. So when we standardize, we're going to divide all through by sigma x bar. So this will give us the probability of x bar minus mu divided by sigma x bar being greater than 10/25, which is the value of sigma x bar, plus the probability of x bar minus mu divided by sigma x bar being less than -10/25. Now, as you can see in this first probability, we need to find the area to the right of 10/25. And since our tables only give us the area to the left, then we're going to take 1 minus the area to the left in order to find the area to the right. So this is now equal to 1 minus the probability of z less than 0.4 plus the probability of z less than -0.4. So from the tables, we find the probability of z less than 0.4 as 0.6554 and the probability of z less than -0.4 as 0.3446. So we replace these values into our equation and find that now this becomes equal to 1 minus 0.6554 plus 0.3446, and we find our final answer as 0.6892. In the next video, we're going to continue looking at how to apply the characteristics of the sampling distribution of the sample mean when we sample from the uniform distribution.